Okay. So 2B, we're on to what's called simple differentiation. So one thing we'll emphasise in 2A, first principles, it's a skill that we do need to know, albeit it's the long way of arriving at a derivative function, okay? So just by way of recap, we have this table at the top where we have y and f of x, they're the same thing, that's the function, right? We input an x value and it tells us the corresponding y value. And then through the process of differentiation, we can arrive at the derivative function, the slope function, the gradient function, okay? So all of those words mean the same thing. Putting an x value into the derivative function tells you the slope, tells you how steep it is for a given value of x.
On a test, if you get given f of x, and you write dy over dx, and you lose a mark.
No, we wouldn't take a mark off, but use the correct notation. So if we have f of x, the correct notation is f dash of x. If we have y, the correct notation is dy over dx. It'd be pretty harsh to take a mark off, but speaking of tests and so forth, the way we mark a test is the performance standards, and one of the performance standards is about correct notation. So just be consistent, do the right thing. There's things in tests called trivial errors. I would argue that's a trivial error. All right, so let's get straight into it. Firstly, we have the table of rules there. So if we have x to the n, if that's our function, then we have the derivative function is n x to the n take 1. So we definitely learned that rule last year. If we have kx, then the derivative is k. Now that's a direct application of this rule, although it can be a little bit hard to see. That's why I set it out as a separate rule. And if we have a constant, then the derivative is 0. So we'll get straight in here. If we have y equals x to the 7, then we are going to write 7x to the 6, okay? N comes down, so x to the n, x to the n take 1. Now I've intentionally left out our correct notation here because this is where you get marked down for notation. Is if you write here's y and this is what it equals. These are not the same function. We have performed differentiation here, so therefore we need to state dy on dx is 7x to the 6. Here's the function, here's the derivative. Okay, we're very clear about they're not the same thing, we've performed something to it. Okay, on to b, and we have y equals 4, take 3x to the 4 plus 6x. So I'm going to go through and do all of these the long way, although this is a 1 mark question, all right? So the derivative of 4 is 0, okay? 4 is a constant, the derivative of a constant is 0. Then I've got minus 3, and I'm just going to open up a bracket because anytime we're multiplying something, like here we have minus 3 times x to the 4, I've got minus 3 times, and I just go, what's the derivative of x to the 4? 4x to the power of 3. All right, and then for kx, the derivative of kx is k, so the derivative of positive 6x will be plus 6. So all of that's the long way, the elongated way of saying minus 3 times 4 will give us x to the 3. That is our derivative function. Okay, now make sure we use the correct notation. Now, maybe I'll just say as well, this one here is not completely necessary. We've gone from y to dy over dx. This is the derivative function here. And in the next step, it is equal because all we've done is simplify it a little bit, right? We've multiplied them out together. Now, on to c. So for c here, we have y equals, we've got 4x squared plus 7x multiplied by x take 2. Now, in order for us to perform simple differentiation, there's a few things we need to make sure. So I'll just point out the process that I've highlighted in the middle. Firstly, we need to ensure that all terms are expressed in the form x to the power of n. So if we look along here, everything is in terms of x. All right, that's x to the 0, x to the 1, x to the 1, x2. So we're sort of satisfying that first one. But in the second after the comma, the function is fully expanded. Okay, so that means we're going to need to perform our FOIL here to fully expand this out before we differentiate it. So when we expand this out, we have 4x to the 3, so we multiply the first terms, the outside terms, the inside terms, and then the last terms. Then we'll collect like terms, so we've expanded, now we'll collect, so we're just simplifying it a little bit. And it's going to be take 1 lot of x squared, minus 8 lots of x squared, plus 7 gives us that minus 1. Okay, now we haven't actually done anything here. All we've done is expand and collect it. It's still the same function. Look, equals, equals, equals. Now we're ready to differentiate. Everything's at the top of the fraction, x to the n, fully expanded. So we go dy on dx, the derivative function. And here, I'm just going to go straight to 12x squared. Take 2x, take 14. Okay, so for now, when we have sets of brackets, we need to fully expand it before we differentiate it. Okay, let's have a look at D. So up here, we have fraction. And we've got here y equals x squared take 4x on top of x. So, just having a look at our process again, it says, in short, everything is in the form x to the n, the function is fully expanded, and at the top of the fraction. We've got this denominator, which means if we're going to apply simple differentiation, we need to get rid of it somehow. Now, one thing we can do, one of our legitimate fraction operations is like, we know this is sort of arbitrary. If we have, 3 take away 1 on top of 4, we could write that as 3 on 4 take away 1 on 4, right? We can split the denominator, okay? Or you can think about it, if I'm performing this fraction operation, I can collect them together over the same numerator. That's what we're going to do here. We're going to split the denominator, okay? So there's lots of ways of doing it, but I just want to draw out that skill in particular here. So we have x squared on x, take away 4x on x. Okay, and now we're going to simplify each term. So on the left-hand side, we've got x squared divided by x, that will simplify to x. And on the right here, we have x at the top, x at the bottom, that will simplify to 4. That's still the original function. Now we differentiate, so we've got y, dy on dx, okay? And this is 1x, the derivative of 1x, 1. Really good. Okay, on to f. F of x. Now we have 2 root x plus 5 on top of x root x. Okay, so our first step, we're going to express it all at the top of the fraction as x to the power of n. Now, we should remember the square root of x is x to the power of a half. So that means at the bottom here, I have x times the square root of x. So that means x times x to the half, right? And x by itself has a power of 1 on it. So the way we simplify that, the same base, therefore we can add the powers together. 1 plus a half, 1 and a half. 3 divided by 2. Okay, so anytime, this is a rule, it's going to pop up a lot. Anytime you see x root x, that simplifies to x to the 3 on 2. Now I'm going to do this over 2 steps, just to draw out those index laws. So the first thing we have is that term, the first term becomes 2x to the power of a half, and the second term becomes 5 on top of x to the power of 3 on 2. All right, I'm doing it over 2 steps. The next step, so I've expressed everything as x to the power of n, that's done, but this term's at the bottom of the fraction. Therefore, we need to take this one to the top. And remember, we can do that provided we make the power negative. So this one's going to become 5x to the minus 3 on top of 2. All right, we're taking it to the top and making the power negative. Okay, so here's our function. This is one way of writing it. Here's another way of writing it. Here's another way of writing it. All of these are the same thing. Now we can differentiate. So we go from f of x to f dash. All right, and this one, again, I'll do this one slowly. So the multiple just stays out the front. The derivative of x to the half, we just follow that same rule. X to the n, it becomes n x, and then half, take away 1, that's going to be minus half. So we're just following that same rule. The same with the 5 term. I'm going to have 5 there. All right, 5's the product, and then we have minus 3 on 2, x to the power minus 3 on 2, take away 1, minus 5 on 2. So those kind of fraction operations I can show you. You can use your calculator, but we should be pretty comfortable with them by now. Okay, next we are going to simplify our answer. Now this is a good opportunity for me to talk about in the upcoming test, so in about week 6 or so, week 6 or 7, when we're looking at an answer, you're getting full marks here, all right? However, you do need to know the algebra involved in simplification. And if you're checking your answers in the textbook, they won't answer it like this. They will simplify every single time. All right, so it can be a little bit annoying because you're getting full marks here, and in the exam situation, you get full marks here. But the textbook does like to go ahead and simplify things. So I'll show you how the textbook tends to express it. All right, so firstly here we have 2 times a half. That's going to just become 1. So we've got that they is effectively cancelled. And we have x to the minus half. Now the way they express that is they put it at the bottom of the function with a square root. So they revert back to the surd presentation of it. Rather than it being a power, it becomes a surd. Now it's the square root because the power is half, and it's at the bottom because the power is negative. What goes at the top? 1, all right? 1 because we've got one lot of it. Very good. Okay, same here, this term. All we should think about is multiply the numbers together. So 5 times minus 3 gives us the minus 15 at the top, and we have 2 at the bottom. And then we have, let's do this one over 2 steps maybe. We have x to the power of positive 5 on 2 at the bottom. Now the way the textbook will express that one is x squared root x. All right, and the reason they express it like that is because x squared times x to the half. All right, you add the powers together. 2 plus a half is 2.5, which is 5 on 2. So you can see that they're equal, but you're getting, again, you're going to get full marks at this step here. Okay? All right, so you open up the test. On the first page, it's going to say, differentiate the following without simplifying. So all you're required to do often is manipulate it a little bit, differentiate, full marks obtained right there.
Will you lose marks if you mess up in the simplification?
No. So once you've gained marks, you can't then go ahead and lose them. Yep. So you've gained the marks by showing.
So you don't actually have to solve anything, you just rearrange it and then move it around and that's it.
That's the first page of the test.
Yeah.
It does get more complex than that.
If
But
we get the answer wrong, we get simplification right.
you can get a mark here for simplifying. Yep. And then.
If we get that right, double tick.
So if you get the differentiation, right?
Yeah. So all right. So if you simplify wrongly, but then differentiate what you've done wrong correctly, you'll still get a mark. Yep. Because that's called what we call, and you'll see me when I'm marking the test. I'll write this kind of thing next to it: error carried forward. So if you make an error here, but then perform the correct mathematics with the error you've made, you're still demonstrating understanding of the mathematics. So you can still earn marks even if you make mistakes. Absolutely. As a marker, right? You know, having marked for SACE for a number of years. We're on your team, right? And our job is to get you the marks. You just have to show that they're there. All right, so even if there's an error carried forward, you can still get those marks. All right, so our plan today is just to be. It's good exercise and it should be a good confidence booster. And we've got lots of time for me to float around and have a chat to everybody.